Alright, this is exam 1, physics 202, spring 2017. Gravitational field. Fields are always some force per unit something. It's force per unit mass. The escape velocity is based on the law of conservation of energy. Here we have field lines going through a Gaussian surface, but at an angle. Now, if they were going perpendicular, since this is 2 square meters, and this field is equal to 10 meters per second squared, if they were perpendicular to one another, the field to the area, the answer would be 20. But here, since they're offset by an angle, it'd be some value less than 20. Here, two masses experience a gravitational force. What happens if you bring them closer together? Well, if you bring two masses closer together, you get a bigger force, and in this case, it'll be 4 times the force. It's that whole inverse square thing. Atomic particles, electrons, protons, and the like, are made up of subatomic particles. We call these quarks. They have a certain charge, and they have a charge that's actually subdivided from the fundamental unit of charge. And here it gives the charge for an up quark, which is plus 2/3 e, and a down quark, which is minus 1/3 e. Which combination of these makes up a proton, which has plus 1 e? Well, the only combination is 2/3 plus 2/3 minus 1/3, so that is an up, down quark. Makes up a proton. This diagram shows 3 heavily charged plastic cubes. The net force on B is shown. If it's negatively charged, what are the charges of the other cubes? So if it's negatively charged, let's see, my forces, the one due to A has to be in that direction, the one due to C. That's really the only combination of forces that'll give me this resultant vector. And that means that A is negative and C is positive. A is negative, C is positive, so number 6 is C. When you rub your feet on the carpet, you gain electrons from the carpet, and you can pass those on to other people. Which of these is a property of charge? It's quantized and it's conserved, so A is A. Is this statement false? True or false? The electrostatic force helps to hold together heavy nuclei. That's so false. It's so incredibly wrong, because if you get a nucleus with some protons and neutrons, you have immense electrostatic forces that are pushing these things apart. Immense forces. And it's actually the strong nuclear force that holds them together. We talked about that a little bit last year. The force between two charges separated by 4 meters is 18 newtons. What if you move it to 12 meters? Well, let's see, this is sort of a repeat, but that's okay. So I increase my distance by a factor of 3. That means I'm going to decrease my force by a factor of 9. Remember, force is proportional to 1 over r squared. So the answer is 18 divided by 9, or 2 newtons. 2 electrons are spaced equally far apart in a line, as shown. What is the direction of the net force on the second electron? Well, the force on this one due to the proton is in this direction, and due to the other electron is in this direction, so it's going to be to the right. Consider this configuration of charges. At what point is the electric field equal to 0? Let's see, we just want to sort of take each spot. Let's just start here in the middle first. Due to the minus 4q charge, the electric field is in that direction. Due to the plus 2q charge, it's also in that direction. So I can't get anywhere in the middle where the electric field is 0, because they're going to add up. They're both in the same direction. So let's look at E and A and E. Over here at E, due to the minus 4q charge, I get a big electric field. Due to the plus 2q charge, I get a little electric field. So in a similar way, I'm not going to get any 0 electric field to the right of the minus 4q charge. In fact, I'm only going to get it to the left, because notice, if I do my electric field due to this minus 4q, excuse me, that's not right. Due to the minus 4q is in this direction, I'm now further away from that big charge, and due to the plus 2q is in that direction, so A is the right answer. Alright, I have this electron beam that goes into these 2 plates. They're going to move in this direction. You can think about it a couple ways. Really, the best way to think about it is the electric field is in this direction, and electrons move opposite the direction of the electric field. Or you can also think about the forces that are involved. I mean, this is sort of more fundamental. These electrons are repulsive forces. So I have forces in that direction and that direction. And the positive charges are attractive forces. So the actual Coulomb's law describes the direction. Alright, what quadrant does the net electric field vector point? Well, let's consider. Here, let's see, plus 2q is going to be in that direction, minus 3q is also in that direction, and 5q is in that direction. So add those up and it gives me that quadrant. Who is Dr. Young's favorite student? Well, Joe Thibodeau, of course. No, it's me, or it's you, rather. All right. Consider this configuration of masses. The 2 kilogram mass on the left is a point. The 10 kilogram mass is a hollow sphere, hollow shell, or it's a hollow shell. It's a spherical shell. They have a radius of 0.3 nanometers as shown, and they're separated by 3 microns. Determine the magnitude and the direction of the electric gravitational force on a 2 kilogram mass. Well, first of all, the direction is going to be in this direction. So it's going to be in the positive x direction. And then, you know, it's really just F equals G m over r squared, because you need to realize that the shell I could just treat as a mass. So I could have one mass here, separated by 3 microns of 2 and 10 kilograms. So I get 6.67 times 10 to the minus 11, 2 kilograms, 10 kilograms, so just sort of, you know, normal masses, divided by r, which is 3 times 10 to the minus 6 meters, and that's squared. And, you know, that's a small distance, but it's not a terribly small, 3 microns, you know, hair width or whatever, and that's equal to 150 newtons. 150 newtons. You believe that? So you get those things that close together and they're going to be attracted to one another. Look at this configuration of 2 coulombs and minus 4 coulombs, and just draw 6 field lines and then draw the electric force vector. So my field lines are going to go from the plus 2q charge to the minus 4q charge. I drew it that way for a reason. I'll show you here in just a second. And then I'm going to have twice as many lines going into the minus 4q charge, so it'll look like this. You can draw, oh, let's see, well, I asked you to draw 6, didn't I? So now I have 4, I only have 6 going in there, so I need 2 more. Make sure I got this right. I have 4 over here and I have 8 over here. All right, that's good. And I will change this to 8. Or to some other number, we'll see. Alright, now I also want you to show the direction of the electric force. So if I imagine this point P, I have an electric force towards that 4 coulomb charge, a smaller force away from the 2 coulomb charge, so the net force is in the same direction as the electric field vector. Consider this cylinder of mass. Same radius and mass as that of the Earth. Length of the cylinder is 8 million meters roughly. It's a cylindrical planet. Isn't that awesome? You have a cylindrical planet. This would be the Earth if it was cylindrical. And now you know on the Earth that the gravitational field at the surface of the Earth is, you know, roughly 9.8 meters per second squared. So let's see what the acceleration on this cylindrical planet would be. Well, Gauss's law says that phi, which is the flux, is negative 4 pi g mass inside, and that flux is equal to g times the area, assuming they're perpendicular to one another. So we're going to take a Gaussian surface that is a cylinder, a really long cylinder, so we'll just sort of leave off the ends of the cylinder. They're not that important because there's no flux going out them anyway. We'll assume our Gaussian surface is very, very long, and that's equal to negative 4 pi g mass inside. Now we're looking for g, so let's just go ahead and solve this for g. Negative 4 pi g mass inside divided by the area of a cylinder is 2 pi r times h. That's on your equation sheet. And notice that I left off this pi r squared thing. I think it was like, what, 2 pi r squared? I left that off because I've made my Gaussian surface really long, and I don't have any flux lines coming out the ends. So the total flux out the ends is equal to 0, so I just leave that off. Now, pi's cancel, that cancels gives me a 2. I get negative 2g mass inside divided by r and h. So I'm going to put some numbers in there into my cylindrical planet. 6.67 times 10 to the minus 11. The inside mass is, well, it's that of the Earth. Shoot, I don't have it in front of me. It's the mass of the Earth. Is that the Earth? I don't know if that's the Earth symbol. I'll just do mass of the Earth. Divided by the radius of the Earth, which is 6.4 times 10 to the 6 meters, divided by the height of my cylinder, That's 8.5 times 10 to the 6. And I get a slightly different acceleration due to gravity, 14.7 meters per second squared. Even though it has the same density as the Earth, because it's distributed differently, it has a different acceleration due to gravity. A different gravitational field, same thing. What is the electric field at point P? Let's first just draw our vectors. Oops, sorry about that. Our vector due to the 4 nanocoulomb charge is in this direction. Vector due to the 32 nanocoulomb charge is in that direction. Let me redraw that so there'll be more to scale because, you know, I got a bigger charge. It should actually be about an 8th. Now let's calculate first. I'll call this E1. I'll call this E2. And I'll call this E1. Let's calculate what those are. E1 is 9 times 10 to the 9th. I'm doing, you know, KQ over R squared. 9 times 10 to the 9th. Q is 4 times 10 to the minus 9 divided by 2 squared. Cancels with that. That cancels with that. And I'm left with 9 newtons per coulomb or 9 volts per meter. And then in a similar way, notice I'm not putting a negative here. That cancels and leaves me 8, and those cancel, and that gives me 72. So I have 72 newtons per coulomb, and I have 9 newtons per coulomb here. And now I want to know just the magnitude and direction. Well, shoot, you know, I got my vectors, 72, 9. The resultant is going to be here. The magnitude of that electric field is going to be the square root of 72 squared plus 9 squared, and that's equal to 73 newtons per coulomb. And then theta, which is this angle right here, is the inverse tan of 72 over 9, which is 83 degrees below the negative x. All right, so that's the answer for the first one. You place an electron at point P. What force does it experience? Well, F equals QE, right? So that's 1.6 times 10 to the minus 19 coulombs, that's the charge of an electron, times 73 newtons per coulomb. And that gives me 1.2 times 10 to the minus 17 newtons. And then part C, I want to know what are the direction and magnitude of the initial acceleration. Well, let's pull out some Newton's second law. A equals F over m. And remember, force per unit mass is a field, a gravitational field, and so that's where we get our value for G. It's actually gravitational field. And if I do this, that 1.2 times 10 to the minus 17 divided by, that's newtons, divided by the mass. What are we dealing with? An electron, 1.67 times 10 to the minus, excuse me, that's a proton, 9.11 times 10 to the minus 31 kilograms, and that gives me 1.3 times 10 to the 13th meters per second squared, and it's going to be in the same direction as the force, so 83 degrees below the negative x-axis. Did I say? Yeah, below the negative x-axis. So that's the answer for that part. Did we answer all the parts? Oh, is there a place where the electric field is 0? Well, let's look at this. Is there a place where the electric field is 0? Well, you know what? It's going to have to be somewhere along this line. I want to be far away from the big charge, but closer to the little charge, so it's going to be like right there, somewhere along those, on that side of the 4 nanocoulomb charge. Oh, there's one more question. All right, so a beam of electrons between 2 charged plates separated by 0.1 meter. They have that speed, and they enter a position equidistant from both plates. The electric field has a magnitude of 0.2 newtons per coulomb. What are the lengths of the plates, and what is the direction of the electric field? I'm sorry, I actually changed this. Do the electrons go up or down? And I'm actually going to have to stop here to go to class, so I will stop this and I'll come back and work it later. Okay, sorry for that interruption, but continuing on, and I'm actually going to change this a little bit. I'm going to have the electric field lines drawn in the upward direction. So as you're thinking about this, you know, I got this beam of electrons. They're going to travel in a direction that is opposite the field line. So what I need to do is find the time that it takes for it to travel this distance of 0.05 meters, and then when I find that time, find what is the time it travels this distance. So, and then I'll use that time to figure out what distance does it travel. So, first thing I want to do is I know the electric field is 0.2 nanocoulombs. So the force of the electric field on the electrons is equal to Q times E. That's 1.6 times 10 to the minus 19 coulombs times the electric field, which is 0.2 newtons per coulomb, and so that gives me 3.2 times 10 to the minus 20 newtons. That's the force on each individual electron, and then the acceleration of each individual electron is going to be F over m. That is that force, 3.2 times 10 to the minus 20 newtons divided by the mass, which is 9.11 times 10 to the minus 31. That would give me the acceleration in the y direction, which is 3.5 times 10 to the 10th meters per second squared. Again, this is in the y direction, so I'll go ahead and put my vector on there, and it's also in the negative y direction because I know it's opposite the direction of the electric field, just the way that I've drawn it, so I have a vector there. Now, it travels a distance of 0.05 meters. The total width is 0.1 meters, so that's just half that value, 0.05 meters. And I know that the initial velocity in the y direction, that's equal to 0. And now I know the acceleration. I can say y equals 1/2 at squared and solve that for t. And I find that that's equal to the square root of 2 times 0.05 divided by the acceleration. I'm leaving the negative off here because I'm just looking for the magnitude here. I just need the magnitude of the acceleration. And that's going to be 1.69 times 10 to the minus 6 seconds. 1.69 microseconds. And now I can find the distance that it travels in that time. As a final step, is going to be the velocity, which is 2 times 10 to the 4th meters per second, times that time. And that'll give me my final answer, which is 0.034 meters, or if you want to express it in centimeters, that's fine, 3.4 centimeters. You know, so this little chamber is about that long, and the electron travels a tenth, you know, about that far. So these electrons, sort of to scale, are traveling along in that distance, approaching the end of the tube. I think that was the last one. Yeah, there we go.